If x is a discrete random variable with probability mass function f of x, we can find the mode by evaluating f of x at its possible values and finding the values with the greatest probabilities, or computing the ratio between successive probabilities and finding where this ratio changes from greater than 1 to less than 1. Both of these require a lot of work. Is there an easier way? While the PMF is only defined at discrete values of x, f of x can be viewed as a continuous function. And if we want to find the maximum value of a continuous function, we find the derivatives, find the critical values, and determine which critical value corresponds to the maximum value of our function. Now, calculus is generally easier, but this requires us to be able to find the derivative. So suppose x is a discrete random variable with PMF, find the mode, we'll find the derivative, and here we have to remember the derivative of an exponential function is the critical values occur when the derivative is 0, and so we find now, since x can't actually be a decimal, we can round down, and this means that x must be 3. Or does it? Without more details of the local behavior, we don't know the relationship between f of 3 and f of 4, so we'll compute both. We find the probability that n equals 3 will be and the probability n equals 4 will be and so we find that x equals 3 and x equals 4 are equally the most probable, and so the modes are x equals 3 and x equals 4. As the previous example shows, we can't simply round the critical values to determine the mode. While the mode is one or both of the possible values adjacent to the critical value, we can't generally determine which it is without further analysis. But if our random value is continuous, then it can take on the critical value, so it will be our mode. For example, suppose the lifetime of a light bulb has density function proportional to over the interval 0 to 5 and 0 otherwise. Let's find the mode. So we want to find the greatest value of f of x, so we'll differentiate. And note that because the proportionality there's a constant here, but because we're differentiating, we can remove that constant and find our derivative. So we'll use the quotient rule to get next, we'll find our critical values. The critical values occur where the derivative is 0 or undefined, and note here that because that's a multiplied constant, when we set the equation equal to 0, we can drop out that constant and our denominator. And since x is greater than 0, we can divide by x, and so we obtain we also need to check the endpoints. While the PDF is actually 0 at the endpoints, we should find the limit as we approach them to allow for the possibility that the probability increases as we get close to 0 from above or 5 from below. We'll use the notation 0 superscripted to indicate that we're coming at 0 from above, and that turns out to be 0. If we approach 5 from below, our limit is, and we can also evaluate f at the actual critical value, which will be, and so checking our endpoints and critical values we get, and the greatest value occurs at x equals 1.26, so this is the mode. We could have another function. So again, we'll differentiate. We'll set the derivative equal to 0 and solve. And since this is a product, we can set each factor equal to 0. So that first factor equal to 0 gives us a critical value. The second factor equal to 0 we can solve. And this gives us two solutions, but the second solution is out of the range, so we'll ignore it. So we'll find the values at the critical values. We also need to check the endpoints of the interval. And again, we're really finding the limits as we approach the endpoints. And so we find And so we see that the greatest value is going to be at 0.7753, so that's the most probable value and the mode.